What we did in the first part of the talk is that we showed that any AC0 circuit of small size and depth has a low error, low degree probabilistic polynomial, right? And the precise statement was this: any circuit of size S and depth D. So I'm going to use this notation AC0 SD for circuits of size S, depth D. Any circuit of size S, depth D, AC0 has an epsilon error probabilistic polynomial of degree something like polylog S times log 1 over epsilon. Okay, this construction, the one that I described, was over F2, right? We use the fact that if you're not saying 0, you're saying 1 really. So that's where we use the fact that we're working over F2. But it turns out it's not very hard to port this proof to other fields. So for example, we could have worked over Fp, the field modulo prime p. We would have paid a factor of p in order to convert a non-Boolean output to a Boolean output and just keep repeating the same argument. So you get an upper bound of something like order p log s to the d minus 1 times log 1 over epsilon. This is useful, for example, if you're working with AC0 with mod p gates. Then you want to approximate things over Fp because mod p functions are low degree functions over Fp. Right. There's also a version of this argument that works over any field, for example, over the integers. Right. This is a slight modification of the basic OR construction. It's very similar, but there is an additional idea involved. But nevertheless, the parameters are not very different. It looks like something like order log s to the 2 times d minus 1 times log 1 over epsilon. Okay, so these are all probabilistic polynomial constructions that we have. And from this we get a corollary. So for example, from the theorem we get the following corollary. Recall that whenever we have a probabilistic polynomial, by fixing the randomness we can always get an epsilon approximation of the same degree. What that implies in this case is that in particular any circuit, AC0 circuit of size s and depth d, has an epsilon approximation of degree log s to the d minus 1 times log 1 over epsilon. Just to remind you, an epsilon approximation is a fixed polynomial that agrees with the circuit on a 1 minus epsilon fraction of its inputs. Okay, all right. So let me give you the kind of first and classical application of this theorem in circuit complexity to prove a lower bound, right? So what we are going to show now is that the majority function does not have a 0.1 error approximation of degree less than square root n. Okay, so right, what does that mean? Any polynomial that agrees with the majority function on at least a 90% of its inputs has to have degree at least roughly square root n. Okay, so if you plug the parameters in and work out the lower bound, what you will see is that this implies that any AC0 circuit of size s and depth d for majority, so let me write it here, a corollary of this corollary and that theorem is that any depth d AC0 circuit for the majority function on n bits has size exponential in n to the 1 over 2 times d minus 1. Okay, there's a constant factor here which I'm omitting. This is not quite tight. There's a better bound due to Johann, but it also holds for a larger class of circuits. So for example, if I augmented my AC0 circuits to also contain mod 2 gates, for example, mod 2 gates, parity gates also compute low degree polynomials over F2. So this entire machinery would go through for AC0 with parity gates, and you would also get a similar lower bound for that stronger circuit class. Okay. All right, so this theorem. Okay, so how are we going to prove this? Well, the way I'm going to do it is by introducing another notion of polynomial approximation. Okay, so what is the notion I'm going to introduce? So this thing, I'm going to call this a certifying polynomial for a Boolean function. Okay, so what do I mean by a certifying polynomial for a Boolean function? So let me say that P is certifying for f if it satisfies two conditions. Okay. The first is that p is a non-zero polynomial. Okay, it's a non-zero multilinear polynomial. And the second is that at every point, so let me say this correct, at every point that p is non-zero, f takes some fixed value. So there exists a b in 0, 1 such that at every point where p is non-zero, f takes the value b. Okay. So you can think of p as certifying that f takes the value b, right? Whenever p is non-zero, that implies that f takes the value b. Okay. So if I wanted to say this in pictures, I would draw the hypercube. Right, this is the hypercube. And think of f as partitioning the hypercube into two parts. So this is f inverse 0 and f inverse 1. Okay. So what p is doing is that p, its support of p, so let me define the support of p to be the set of points where it's non-zero. Its support is either contained here or here. Yeah, so right, or this. Okay, so when p is non-zero, either f is fixed to be 0, which means the support is contained in here, or when p is non-zero, the support f is fixed to be 1, in which case the support is in here. Right, is this definition sort of clear? Okay, so maybe let's just see a couple of examples. Maybe one example, the AND function, is a simple example. Okay, so but before I say that, let me just kind of clarify that I'm making no assumptions about how many places p is non-zero, right? As far as I'm concerned, p could be 0 almost everywhere. It's just that on the support of p, f is fixed, right? So there is no assumption on the error of this polynomial approximation. Okay. All right. So, for example, take the AND function, right? Now we could, so I'm going to give you a certifying polynomial for it. Of course, I could give you the polynomial itself. That would be a certifying polynomial, right? But that would be of degree n, but I want a low degree certifying polynomial. So I want to certify that AND is some value, and I want to do it as easily as possible, right? So for the AND function, the natural thing to do is to certify that the AND function is 0, right? Because easy to make the AND function 0. So I could take, for example, the polynomial, I don't know, 1 minus x1, right? So if this polynomial is non-zero, that means x1 is 0 and the AND function is forced to 0, right? So this is a certifying polynomial for the AND function of degree 1. Okay. Any questions about this? All right. So how am I going to use this? Well, to use this, what I'm going to do is construct certifying polynomials for functions in AC0. Okay. But just before I do that, I want to understand this complexity measure a little more. Okay. Let's start with constructing a certifying polynomial for any function. Okay. So now let's say f is just an arbitrary Boolean function. And what I want is a certifying polynomial for f of low degree. Okay. And once again, I could just write down the polynomial expression for f, and that would be a certifying polynomial. It would certify that f is 1, but I want to do something better than that. Yeah, so I would like a low degree certifying polynomial for f. Okay. So how low can I go? Yeah. So let's just try to understand. So suppose I want, say we want a certifying polynomial of degree d.
Srikanth, what is the field?
Okay, good. It doesn't matter for this part. It doesn't matter. For the lower bound, I'll probably use f2, but it doesn't matter.
So the degree of the certifying polynomial is a field independent quantity? Is that what you
It could of course depend on the field, right? But the lower bound will be field independent. Okay. So say that we want a certifying polynomial of degree d, okay, where d is some parameter that we'll choose, right? Well, what would we do, right? So our polynomial could either certify that the function is 0, or it could certify that the function is 1. All right, we could either ask for a certifying polynomial like this, or we could ask for a certifying polynomial like this. Okay, so now what are we going to do? So what should we go for? Well, let's say we wanted to certify that the function is 0. Okay, just for definiteness. So what we want is, I want to write down this polynomial. It's got to be of degree d. So when I write it down, it's going to look like this. Yeah, and I wanted to certify that my function is 0. So what I want is that p of a equals 0 for all a in f inverse 1, right? So I wanted to certify that my function is 0, so I want it to be 0 when my function is 1, right? So when the polynomial is 1, if the polynomial is non-zero, it certifies that my function is 0. Okay, right? And I want to find these coefficients so that this is true, right? And the final constraint, of course, I would want my polynomial to be non-zero. All right. So what I'm really trying to do here is solve a system of linear equations, right? I want to find the coefficients of these monomials. So I'm solving a system of linear equations. The number of variables in this linear system is something like n choose 0 plus n choose 1 plus n choose d. Right. And the number of constraints is cardinality f inverse 1, right? To assure myself of a non-zero solution to the system of linear equations, all I need is that the number of variables is greater than number of constraints. Okay. All right. So, well, how do I arrange for this? The only way I can arrange for this is by choosing my b suitably. So I could either choose to certify that the function is 0, or I could choose to certify that my function is 1, right? If I choose my side carefully, I can ensure that my constraints, the number of constraints that I have is at most half the number of points. Yeah, so I can ensure. So right? So how would I do this? Well, I start with f inverse 1, but if there are more than 2 to the n minus 1 constraints, then I switch 1 to 0 and I work with f inverse 0 instead. Okay, so I can always ensure that the number of constraints at most 2 to the n minus 1. So I need to choose my degree parameter d so that the number of variables at least 2 to the n minus 1.
Don't you need to ensure that the rows are dependent, because otherwise there might be a contradiction?
So this is a homogeneous system of linear equations, so there's only no contradiction. So the all zeros is always a solution. It's the only problem is to get right. Okay, exactly. So good point. Yeah, it's a homogeneous system.
So does that mean it's basically hopeless for any unbiased function?
Sorry, it's hopeless for any unbiased function? No, no, it's not. But it's hopeless for some unbiased functions. But yeah, so you can do better. In fact, for functions that have small circuits, there is a better construction, and that's kind of what the bound is based on, the lower bound. Any other questions? Okay. So we can ensure the number of constraints is less than or equal to 2 to the n minus 1, which means that if I want to ensure that my number of variables is greater than the number of constraints, I need to choose d roughly n over 2. Let's say n over 2 plus 1, but I'm going to say, yeah, let's say n over 2 plus 1, right? Because if I choose d to be n over 2 plus 1, the number of monomials of degree at most d is going to be this binomial sum, but I go all the way till n by 2, and that's like 2 to the n minus 1. So what have we shown as a result of this? So, well, we've shown this fact: any f has a certifying polynomial of degree, let's say n over 2 plus 1 maybe. Okay, right? So which is a slight improvement over the trivial bound of just representing the function as a multilinear polynomial, right? If I just write it out as a multilinear polynomial, it has degree n. Now it's slightly better, it's like n by 2. Okay. So you can ask now, can you do better than this? Can you actually show that every function is has a certifying polynomial even lower degree? And the answer is no. So this fact is actually tight for the majority function. Okay. So any certifying polynomial of degree smaller than n by 2, I'm sorry, any polynomial of degree smaller than n by 2 cannot be a certifying polynomial for the majority function. Okay. Yeah. So maybe some people see a proof of this already from what I've said or independently, but let me go through the argument anyway. Right. So just to recall, here's the picture of the hypercube. What does the majority function do? Well, it kind of splits the hypercube into two parts. This is the 1, this is the 0. Okay. So if I had a certifying polynomial for the majority function, well, what would it have to do? It would either have to be 0 everywhere here and non-zero only here, or it would have to be non-zero everywhere there and non-zero only here. Right. Either way, it would have to be 0 on a Hamming ball of radius n by 2. Right. So this would have to be a non-zero polynomial that vanishes on a Hamming ball of radius n by 2. Either it would have to vanish on this Hamming ball because it's non-zero only here, or it vanishes on this Hamming ball because non-zero only here. So it vanishes on a Hamming ball of radius n by 2, and we saw already, right, an hour ago, that any non-zero polynomial of degree d cannot vanish on a Hamming ball of radius d. Right. So in particular, this polynomial will have to have degree more than n by 2. Okay. Does it make sense to everybody? I mean, it's clear. Okay. Okay. So yeah. So a point I'd like to get across here is that so when we are trying to prove lower bounds of parity, for example, it's very natural to work with random restrictions because in some sense they are things that parity is robust against. Right? It's a complexity measure with respect to which parity is as hard as can be. Similarly, this kind of degree is something for which the majority function is as hard as can be. Right? So every function has a certifying polynomial degree at most n by 2. For the majority function, this is the best you can do. So in some sense, it's a natural measure to prove lower bounds against majority. Okay. It turns out that if you're working on the -1, 1 basis over the reals, this is also true for the parity function. So it's also natural to prove lower bounds for parity using this and other things. Okay, so all right, so back to our lower bound. So what are we going to do? We're going to use this approximation that was guaranteed to us by Rasborov's theorem in order to and use it to construct a low degree certifying polynomial for the majority function. Okay, and once we do that, we'll have a contradiction with the statement here. Okay, so let's just do it. Right, I should say that this notion of a certifying polynomial is kind of it's closely related to this is in slightly different language than you'd probably find in the literature or in maybe lecture notes, but it's closely related to certain circuit lower bound proofs of say here Aspness, Beagle, First, and Rudich. So they had a similar proof back in '94, but that was for sign representations, which we're not talking about. There's also a paper of Green, Fred Green from, I don't know, mid-90s, I think, who also uses this notion but over finite fields. Okay. All right, so let's prove that theorem there. So say Maj has an epsilon approximation of degree less than square root n by 10. Okay. Yeah. Then let's draw a picture. So here's the hypercube, here's Maj, and the polynomial. So let me give it a name. Let's say P. So degree less than square root n, considerably smaller, and it agrees with majority almost everywhere. So it's here epsilon equals 0.1, right? Sorry. Okay, so it agrees with the thing almost everywhere. What does that mean? Well, the polynomial is mostly going to agree with majority, but there are going to be a few errors. So let's say this is the error region. Right, so this is the set of points E where the polynomial disagrees with the majority function. Right? Okay. So from here we have to construct a low degree certifying polynomial for majority. How low? Well, smaller than n by 2, and then we'll have a contradiction. Okay. So how does this help us construct a low degree polynomial? Well, it's very simple. Because P agrees with majority almost everywhere, it's almost a certifying polynomial, right? It's almost there. There are just a few locations. So what am I going to do? I don't know what to do about these locations. P might be completely off, but I can try to zero it out. Right? I can just start with P and just zero it out on the error locations. When I zero it out on the error locations, the resulting polynomial is only going to be non-zero up here, right? Because P is already 0 down here. I'm going to modify P to make it 0 here, and then the polynomial is going to be non-zero only here, and that's going to be a certifying polynomial for majority. Does that make sense? Right? So I'm already 0 down here. I force it to become 0 in the shaded region, then I'm fine. Okay. All right, so that's it really. So the polynomial R of x that we're going to construct is going to be P of x times Q of x, where Q is a non-zero polynomial of low degree, let's say degree D, such that restricted to E, Q is 0. Yeah, Q is 0 at all points inside E. Okay, makes sense, right? So once we have this, we're going to take P times Q, and that will be our certifying polynomial. Okay, so now P has degree, by assumption P has degree less than root n over 10. So it suffices for us to construct a Q which has degree less than, well, I need the sum of the degrees to be smaller than n by 2, something like n by 2 minus square root n, something like that. Okay, that's the kind of Q I want. Okay. So why do I have such a Q? How do I come up with such a Q? This goes back to something we saw a few minutes ago. Again, I'm going to construct Q by solving a system of linear equations. Okay. So the Q I want is going to have the form x to the I, right? I need Q to vanish at every point in the error set. So I have the number of constraints equals the cardinality of the error set, which is at most 0.1 times 2 to the n, right? Because I have a 0.1 approximation, so 0.1 times 2 to the n, right? And again, the number of variables is that binomial sum that we wrote down. Right. And all I need to do is choose my degree parameter d so that I have at least so many variables. Yeah, 0.1 times 2 to the n. Yeah. Does it make sense? 0.1 times 2 to the n. Okay, good. So how many, what's the degree parameter I need? Well, this is again going back to what we saw some time ago, right? So we saw that most of the mass of the hypercube, well, probably it goes back to something else. It's easy to check that something like d equals n by 2 minus square root n will do. It's just a binomial estimate. So you just take d equals n by 2 minus square root n. You check that the number of variables you get is more than 0.1 times 2 to the n. So you can find a non-zero polynomial q that vanishes on E. You take the product of that polynomial with your polynomial p, and that will be your certifying polynomial. The degree of this polynomial is n by 2 minus square root n plus the degree of p. Okay? By assumption, this will be less than, by assumption on the degree of p, this will be less than n by 2, and that's a contradiction.
Why is R non-zero?
Ah, fantastic. So I was hoping somebody would ask that question. Why is R non-zero? Okay, so good. Well, let me use that same trick I used there. Q is a polynomial of degree less than n by 2. It's 0 everywhere here, but it can't vanish on a Hamming ball of radius n by 2. So it has to be non-zero somewhere up here, right? So Q times P will be non-zero at that point up there. So it's a non-zero polynomial. Yeah. Okay. Any other questions? Okay, so I'll take that as we are done with this lower bound. So in conclusion, we proved that theorem up there, and what that implies is that any depth d AC0 circuit for majority has exponential size. Yes?
The actual degree of majority, if you want to approximate it?
If you want to approximate, if you actually want to approximate it. So we saw some time back that any symmetric function has an approximation. Okay, so great. So even if I want to get it right with respect to an arbitrary, even if I want a probabilistic polynomial, I can do it with degree square root n. So this is a result of Josh Allman and Ryan Williams. Yeah, good. So any more questions? All right, so right, so actually that last question from Srikanth raised an excellent open problem that that I think would have very nice consequences in circuits. So we don't know of any polynomial for which every approximation must have degrees significantly larger than square root n. Okay, so as I mentioned to Srikanth, so majority has probabilistic polynomials of degree order square root n. It turns out that every symmetric function has probabilistic polynomials of degree order square root n. And improving the square root n to n to the 0.51, for example, has some interesting consequences. Okay.
So is that like a candidate function?
Is there a candidate function? I don't know, but so I know a bunch of non-candidates, symmetric functions, linear threshold functions. These are non-candidates. Inner product is a non-candidate because it's just a parity with degree 2 ands inside it. A random quadratic over F2 perhaps, I'm not sure. All right, so great. So we've concluded the lower bound. So what I'm now going to do is give a different application, a very, very different kind of application of this probabilistic polynomial framework to algorithm design. Okay, and this is something that's been as far as I know, pioneered by work of Ryan Williams, and there have been lots of such results in recent times where probabilistic polynomials for circuits have been used to give algorithms for problems that don't seem to involve circuits at all to begin with. Okay, so lots of interesting results in this direction. I'm going to give you a result of this form for a problem that does involve circuits, right? But nevertheless, it illustrates the general idea. Okay, so what problem am I going to be talking about? I'm going to talk about the SAT problem. Okay, so let me say AC0 SAT. Okay, and so it's an algorithmic problem. The input to the problem is a circuit C in some AC0. We can assume that some sort of size parameter and depth parameter are fixed beforehand for the problem. Yeah, and the question is C satisfiable? Right? So does there exist an A such that C of A equals 1? All right. So this is obviously a problem with a lot of history and a lot of importance. It's a very important problem. And what is it that we know about this problem? Well, we know that it's NP complete. So barring some unforeseen complexity collapses, we don't expect polynomial time algorithms. But more recently, people have been, the community has been exploring stronger hypotheses than the P versus NP hypothesis, than the P not equal to NP hypothesis. More precisely, people have considered, or at least I think it's reasonably accepted now in the community, that this probably does not have any sub-exponential time algorithm. Okay, so by sub-exponential I mean something like 2 to the little o of n. Like you have to kind of evaluate, take at least time 2 to the omega n in order to solve this question. There's actually an even stronger hypothesis out there, and this thing is called the strong exponential time hypothesis. So let me just talk about it for a brief moment. Strong exponential time hypothesis, or SET. Okay, and what this says is that any algorithm, so I'm going to give you a rough idea, this is not quite precise, but any algorithm for AC0 SAT on depth 2 circuits of superlinear size, right? So I just look at depth 2 circuits of superlinear size must take almost exponential time. So time something like 2 to the n minus little o of n. Okay. So if you have an algorithm that solves satisfiability just for depth 2 circuits, so essentially CNF formulas for example, right? And the CNF formulas just have a superlinear number of clauses, so something like n log n clauses. Any such algorithm must take time more than 2 to the 0.99 n or 0.999 n, 9999 n, etc. Okay. So this kind of hypothesis in the literature is called the strong exponential time hypothesis. I think it was introduced in a paper of Impagliazzo and Paturi, right? IP 2001. Okay. Still kind of a, I think a slightly controversial hypothesis. I don't know how well accepted this is. But just to give you an idea of what kind of running times one might expect for the AC0 SAT question, right? So this is a really hard question. In particular, for the case that for the case of depth 2 circuits, we still do not have algorithms running in 2 to the 0.9 n time. Okay. So for algorithms that are so hard, what kind of things can we expect? Well, we can still expect to do slightly better than 2 to the n. Okay. So more precisely, we're going to look at running times that are in the range of 2 to the n divided by a large number. Yeah. So we look at algorithms with runtime 2 to the n minus some hopefully large number. Okay. And this T of n quantity is called the savings of the algorithm. Right? In the sense that this is how much the algorithm is saving over brute force search. If the algorithm had to look at all the inputs, then that would be something. But here it doesn't really have to look at all the inputs. Intuitively, it's looking at only so many, so that's kind of the savings. All right, so what's the theorem that we are going to prove? So this theorem is, as of now, unpublished, I think. It was told to me by Ryan Williams. And I have his permission to talk about it here. So, and it says that, so there is an AC0 SD SAT algorithm running in time 2 to the n minus n over some polylog in the size of the circuit. So you can get running time slightly better than 2 to the n, and the savings something like n over polylog in the size of the circuit. Okay, so if you think of the circuit as being polynomial sized, which is kind of usually what you should do, this is like n over polylog n.
This is a randomized algorithm.
Yeah, it's a randomized algorithm. Yeah. Let me just say right.
And in the hypothesis, it should be deterministic in the hypothesis.
I don't know if there is any sort of consensus on that. So I think getting a randomized version of this would be very interesting as well. I mean, contradicting this hypothesis, getting a randomized algorithm would be quite interesting. Okay. So what's the idea behind this algorithm? Well, it's very simple. So the basic idea is that a circuit looks really complicated, but the analogous problem in some sense for polynomials is easy. Okay, so now you take your circuit, convert it to a polynomial, and then just run the polynomial algorithm. Okay, in some sense, right? And so let me kind of expand on that. So we are going to use inside our algorithm a subroutine which answers an algorithmic question related to polynomials. What's that algorithmic question? Well, it's just the problem of evaluating a polynomial on lots of points, the fast Fourier transform. Okay, so fast Fourier transform. So what I have here, there's another algorithmic question, is I have an input. As input, I'm given a polynomial. So let's say p of x, let's say x1 to xn, which is sum, and I'm given this polynomial just by a list of its coefficients. I don't assume anything about its degree. Okay, so oops, x to the I. I'm just given this list of coefficients, and the question or the output, the desired output, is the set of all evaluations of p on the hypercube. So output p of a for a in 0, 1 to the n. Okay, so just like your normal fast Fourier transform, only instead of evaluating on the real line, you evaluate on the hypercube. It's a multivariate version of it. Okay, and it turns out there's a pretty quick algorithm for this. So what you would expect from the normal Fourier transform, right? So usually you want to evaluate a polynomial of degree n on n points, and you can do it in time quasi-linear, something like n log n. Similarly, here you have a polynomial of, well, the description of the polynomial takes size 2 to the n, so 2 to the n coefficients. You want to evaluate it at 2 to the n points, so you need time 2 to the n, and you can do it in almost that kind of time. So something like 2 to the n times log of 2 to the n, which is like almost more or less 2 to the n. Okay, so here's a simple algorithm to do this. So let me just say eval p n. Okay, it's just the FFT algorithm, and it's a very, very simple algorithm, so I'll describe it. So what am I going to do? I'm going to just take my polynomial. It's a recursive algorithm, right? I'm going to take my polynomial, I'm going to write it in two parts. I'm going to split its coefficients into two kinds. Those that contain, say, the first variable, and those that don't. Yeah, so let me call this part p1 and this part p0. Okay, so p1 is all those monomials that contain the first variable, p0 is all those things that don't contain the first variable. So consider the following. So observe that on inputs where the first variable is set to 0, p1 doesn't really matter because all these terms disappear. So you just have p0, right? So what I should be doing is kind of to evaluate my polynomial on all inputs with the first variable set to 0, I just need to evaluate p0. Yeah. On inputs where the first variable is set to 1, what happens is that the first variable disappears from this and p1 just gets added to p0. right? It's just like I'm substituting x1 equals 1 in here, right? When I substitute x1 equals 1 in here, the resulting polynomial is just p0 plus p1. So okay, and the output is just putting these things together. So that's the algorithm. Very simple, right? So you have this list of maybe 2 to the n coefficients. You evaluate half of them on an n-1 dimensional hypercube. You evaluate their sum on another n-1 dimensional, on the n-1 dimensional hypercube again, and the concatenation of these two things is the answer. What's the running time of this algorithm? Well, the only thing that's really happening at every recursive step is that you're adding p0 and p1. That's the only operation really. So the amount of time you take is more or less just the amount of time needed to add p0 and p1, which is like linear time, right? You just add things together, and then you need to call things recursively. So if you analyze the running time of this, it's kind of like normal fast Fourier transform, something like n times 2 to the n. I'm going to write that as O tilde 2 to the n, because 2 to the n is like the dominant term. There are smaller terms which are logarithmically as large, but I don't care so much about those. Okay, all right. So just to recap, what have we done so far? So what we want to do is we want to check if an AC0 circuit is satisfiable. What we've done is answer some other question about polynomials. So what question about polynomials? You're given a polynomial, you want to evaluate it at all its points, and we can do that efficiently. Okay, what's the link between this and that? Right? And the link between this and that is of course through the probabilistic polynomials for AC0. So what we want to do is, so what is it that we want to do? So what we want to do is convert our AC0 circuit to a probabilistic polynomial, and then just evaluate it at all its points and check if it's non-zero anywhere. So idea, convert C into probabilistic polynomial, let's say P. So I need to specify the error here, let's say 0.1 error, probabilistic polynomial P, and evaluate P on 0, 1 to the n. Okay. So that's the kind of a first approximation of the algorithm, right? It's a very bad algorithm. Clearly, it's going to take time 2 to the n. That's not something I want to do. I will have to improve on this. I will have to improve on 2 to the n. But before I do that, let me actually analyze the running time of the algorithm and see it is at most 2 to the n. Okay. So what is the running time of this algorithm? Well, there's going to be an O tilde all the time, kind of suppressing factors that I don't care about, polynomial factors typically, right? There's the algorithm required to evaluate P, which takes time 2 to the n, okay? But then there is the initial part where you convert C into a probabilistic polynomial, okay? So how long does it take to convert C into a probabilistic polynomial? This is kind of relevant. I mean, there was a question asked in the first part of this talk, where somebody asked me what do we assume about the sampling complexity of the probabilistic polynomial? And this is relevant here because I really want to be able to get this polynomial P quickly, right? In order to do this, you have to just go back to the algorithm that we just saw, right? The proof of Rasborov's theorem. Kind of convince yourself that it doesn't take too long to sample P unless P is really big. Yeah. More specifically, the amount of time required to sample P is proportional to the sparsity of the polynomial P. Okay. So if P is a really, really sparse polynomial, then I can sample it quickly. P is not very sparse, right? Oh, yeah. Okay. Right. So how much is that? Well, how much is the sparsity of P? Right. So suppose I have a degree D polynomial. The number of monomials it could have, its sparsity could be something like n choose 0 plus n choose 1 all the way until n choose the degree of the polynomial. So this is something like n choose the degree of P plus 2 to the n. So I hope this notation is clear. I mean the sum of the binomial coefficients until the degree of p. All right. So what's the running time of this algorithm? Well, there are two parts to the algorithm. The second part takes 2 to the n time, not great. But the first part only takes, well, if I'm looking at a 0.1 error polynomial, the degree here is like polylog s. Yeah? Think of s as polynomial all the time. S is polynomial. So this is polylog degree. So this is really like quasi polynomial time here, not very much. 2 to the n here, which is a lot. Okay. And now the way we're going to improve on the running time of this algorithm is to see that there is a lot we could lose here, and if you could kind of trade off that loss for gain here, then we are in good shape. Okay, so that's the basic idea for the improvement. We're going to improve things by reducing this at the cost of this, where there's a lot of slack. Okay, so let's go ahead and do that. How are we going to do it? Well, extremely simple. So you take your circuit x1 to xn, and what you do is you convert it to another circuit on a smaller number of variables. Thanks. Convert it to another circuit on a smaller number of variables. Okay, so what we're going to do is take the first r variables and look at the following circuit. Right? I take the first r variables and I take all settings to these r variables. There are 2 to the r settings to these r variables, right? And I just take the OR over all these settings. Okay? The great thing about this is it reduces the number of variables. Fine. It also preserves the answer to the satisfiability question. Right? I don't want to change my circuit and change the answer that I want finally. I want to check if C is satisfiable. C is satisfiable if and only if this new circuit, we call it something, maybe C prime, is satisfiable. Okay? And what is C prime again? C prime is an OR of these circuits. So let me give each of these circuits a name, maybe C sub A. Okay? Right. And the basic idea now is to apply this strategy to that circuit, C tilde, C prime, sorry. Yeah. Okay. So we're going to take C prime and convert it to a 0.1 error probabilistic polynomial for C prime, which I'll call P prime. Yeah, and just run this. And the running time is going to be n choose the degree of P prime, more or less, the number of monomials that can appear in P prime, the sparsity of P prime, plus now here's the important thing, it's 2 to the n minus r because number of variables is reduced. Okay, this is clear to everybody? Okay, and the savings of the algorithm is going to be more or less r, right? So it's going to be r, that's kind of what we can hope for. And so what I want to do is I want to choose r. Okay, I would like to choose r to be big, but when I choose r to be big, this circuit C prime blows up, and therefore it's not clear that I'm going to get a sparse polynomial approximation or a low degree polynomial approximation. So that's the tension here. I want to choose r, I would like r to be large because then that would give me more savings here, but then that would force the degree to be large, so I have to be careful. Alright, so we're more or less done, so let's just choose r. It's clear what r we're going to choose, right? It's going to be n over log s to the d minus 1, but let's just try to explain this choice. Right? Okay, great. So how do I convert C prime to a probabilistic polynomial? Well, what does C prime look like? It's the OR over ACA. Yeah. And now this was kind of related to what Clement was asking in the first part, is that if I just apply my AC0 polynomial, the theorem of Rasborov black box to this, I'm not going to get a very good answer. But I can really use the fact that there's a large OR of small circuits. So that kind of helps me here. So take each CA and convert it to a, let's say, delta probabilistic polynomial of degree whatever the theorem guarantees, right? I'm working over F2 for this entire thing, I should have said, right? And here the delta I'm going to choose is going to be small enough for me to union bound over everything. So delta equals something like 1 over 10 times 2 to the r will be fine. Or maybe let me make it 1 over 20 times 2 to the r, because I want an error of 1 over 10 in the end, right? So just make my error really, really small. And what does this cost me in the degree? Well, I'm going to lose something like r times log s to the d minus 1. That's the loss. Okay. I still have that or on top though. I have to replace that by a probabilistic polynomial. But now what am I going to do? I'm going to go back to the theorem of Rasborov, kind of dig into that and recall that an or has an epsilon error probabilistic polynomial of degree log 1 over epsilon. So I'm just going to replace or by a 1 by 20 error probabilistic polynomial of degree, well, constant. Oh, did I give it a name? No, I didn't give it a name. So let's call this maybe P sub A. Let's call this Q. Okay. And my final probabilistic polynomial P prime is just going to be Q applied to all the P sub A's. Oh, A in, yeah, that's right. 0, 1 to the arrow. Yeah. It should be clear that the amount of error in P prime just by a union bound is something like 1 over 10, and we have the probabilistic polynomial we want. Okay. So what's the degree of this polynomial? It's order r times log s to the d minus 1. Yeah. And what I would like is that this degree is small enough so that this does not overwhelm this, right? So suppose I set it so that this entire thing, this degree is like n by 10 or something. Yeah. If I set things up so that this degree is n by 10, this is going to be like much smaller than this. So I just set things up correctly. This is going to be n by 10 for r equals okay. Okay, that's just a choice of parameters, not very important. Okay. So that's it. So that's the algorithm. So you just set up the probabilistic polynomial, expand it out, evaluate it on the entire truth table, see if there is a 1, and you're done. Okay. How much time do I have left? I have 5 minutes left. So I'm more or less probably done because I won't have time to go into anything else. Just want to make a small observation here is that it's a randomized algorithm, but it's a randomized algorithm that makes a lot of error, right? So what we are computing here, so it's just one subtle point. I'm going to point it out and stop. So we evaluate P prime and see if there is a 1, right? But note the following. So this evaluating P prime gives us this huge truth table. This has size 2 to the n minus r. Okay. So P prime is something that agrees with C prime on every input with probability 0.1, right? So on roughly like a tenth of these inputs, it's going to make an error. Yeah. So there are going to be lots of errors. So it's not clear that this algorithm outputs the right answer. But in order to make sure that this algorithm does output the right answer, what you do is that you just run this algorithm a bunch of times, maybe like n times, and then take the majority vote. Okay, so the final algorithm is to run this algorithm n times independently. Each time you get a noisy truth table and take the majority of these truth tables. All right. So, and the reason you want to do this is that each invocation of this algorithm gives you a truth table that agrees with the actual truth table, but only with probability 0.1 at every location. So in general, every single truth table is going to make lots of errors. But when you run this algorithm parallelly a bunch of times independently, and then take the majority vote across these truth tables, let's say n times, and take the majority vote, then that's going to be right on every input with very high probability. Okay, and that's it. So that concludes the description of the algorithm. Let me stop here. Yeah, thanks.
Questions for Srikanth?
Well, this is, I mean, you said this doesn't appear anywhere, but this is basically the ACC set.
Well,
Like-
the problem, yeah, right. So you could run the, so the ACC SAT thing is just a little bit different because not probabilistic polynomials. The running times will be slightly worse. So this is kind of cleaner because it just uses the probabilistic polynomials of Rasborov. For the ACC SAT thing, you need a more high-powered version of that. That works for ACC, right? I mean, you need Beagle-Turvey. That's right. And as a result, the parameters are all a little weaker. So yeah.
Also, I have a question about the notation. So, why do you denote C belongs to AC0 SD? Why it is AC0?
Oh, so the entire algorithm that I've given only works for circuits in AC0, right? Because I'm kind of approximating these circuits by low degree polynomials. And I only have such a theorem for AC0. But of course, you could maybe start with some other class of circuits for which you have such a result and apply this algorithm there as well.
What do you work for AC0 parity?
It also works for AC0 parity, that's true. Yeah. Yeah. Sorry, that.
Any other questions? Okay, so just a reminder that if you're interested in participating in the open problem session tomorrow, let me know, get in touch, and we'll reconvene tomorrow morning. Let's thank Srikanth.